So this morning I will try to make you understand about probably one of the most complex devices that we use in intervention. Many of us may think that stents and flow diverters are complex to make, but in reality, the microcatheter is the most difficult device to manufacture. And thus, many companies actually do not make much profit while making a microcatheter. Now, first of all, what's a microcatheter? Any catheter with a French size of less than 3 micron is a microcatheter. Not micron, I'm sorry, 3 French is a microcatheter. So 3 French and above become catheters. So we know that several of our diagnostic catheters is 4 French. So it has to be less than 3 French. Now this is a pro grade microcatheter. I just use it as a prototype to make you understand how these are made. If you look at the pro grade, you'll see they are given several colors. Right on the tip, you have something which is translucent. Okay. From here, it turns out to be a blue, and then it gets an even darker blue, and finally you have a hub which will have something really thick fixed to it. Now, all these have been built keeping things in mind. Invariably, every microcatheter will have a transparent hub. If you look at it, you'll realize it is because we have to be absolutely certain as to whether a wire is passing through the hub, or if you're putting a coil, it's passing through the hub. So the first mandatory requirement is it has to be transparent. Then it connects to a sleeve. The sleeve is made later and to fuse the hub and the micro. But the reason they make the sleeve long is so that kinking doesn't take place at this point. Very often when we hold the micro, unknowingly a finger tends to kink these points. We may not realize, so they realize that and they give us a nice stiff thing that is kind of kink resistance. Unless you really want to kink it, you can't. But this point is not so. It can kink, right? Now, if you look at the hub, there is always very important information that will be written on these hubs. For example, here there is a 2.7, which basically means it is the French size of the distal point of the microcatheter. It's the outer ID, remember? And also 130 here means the length. This is a peripheral microcatheter, so the length is 130. Now, to understand a little further, when we are talking about microcatheters, one has to understand that in the making of plastic tubes, now plastic is a generic term. You can have many different polymers that are used, but we generically use it as plastic. Now remember that many of the generic material used in microcatheters are also closely guarded secrets. They would not let it known to the public till the patency is over. So there are two ways in which we make plastic products. One is called injection molding. So if you see a plastic toy, it's an injection mold most of the time. Or for example, if you see a plastic component that looks say like a nut, or if it looks like a plastic square. So basically this is based on what? You have a die, the plastic is injected into the die splits into two halves, opens it and release it. A simple way to understand is exactly how you would make an ice cream stick. You have a mold, you fill it up with water, you freeze it, you open the mold and you get an ice cream, right? An ice, not ice cream, the stick part of it, or what do you call it, the ice stick. So that is a technology that we do not use in making catheters. In catheters, they have a technology called extrusion. So what is extrusion? Basically, plastic comes in the form of granules. This granule is heated up, it becomes liquid, and it's injected over a mold in a continuous length, which is finally cut into pieces. So if, for example, if you see any plastic pipe, even the ones used for water, you know, use it as a hose in your garden, it is using the technique of extrusion. So now the liquid plastic is pushed under pressure over a cylinder which is inside a hollow barrel. Now this is what gives you the tube. But remember, when you're making structures of this size, it becomes very complex to do an injection molding. And I'll tell you why catheter technology is very difficult, because on top of the injection molding system, they also fuse multiple different components. For example, the Pro grade has 3 different zones. A distal zone that is very floppy, an in-between zone which is a little more stiffer, and the proximal zone that is a lot more stiff. You can understand it as you look at it. See the way you can understand as I'm holding this. This one you see is a little more floppy, and I'll show it in neuro micros where this is a lot more prominent. But remember, when people make micro catheter, they have to look several properties in their mind. They keep several properties in their mind. The first property is a property which is called kink resistance. Now, for example, here is this micro catheter. It is going through a very difficult anatomy, but it doesn't kink. Can you see this? It is not kinking. Can you see this? It is taking such a tight shape, but still doesn't kink. So this is, how do you do that to plastic? You have to think of that. How can I make a tubing kink resistant? See, I'm making this tighter and tighter and tighter and tighter and tighter to this point. Even now it is not kinked. Now this is extremely important, because when we go through tortuous anatomy, especially inside the brain, these loops can even become like circles like this. But still they don't kink. So how can you make a catheter kink resistant? So into this injection molding system, they have put braiding. Now this is a helical braid. If you look at it, I don't know if you can see, but if you cannot see, please take a micro catheter and look at it. When you look at it, you'll see there is a spiral braiding that is running. Now the advantage of the spiral braiding, it makes it flexible. It also makes it kink resistant, because the braiding won't allow it. But braiding of this type has a problem of the second property. What is the second property? It is a term called pushability. When I push a catheter, will it go forward? See, this is really flimsy, you understand? Even though there is a wire over it, how can I make it go forward if it's a spiral? The problem with the spiral will tend to compact. So because of that, they change the braiding as we come proximally. So here they have a braiding which is 2 X's running together. Like you'll have braidings like this. You get the point? Now, one thing we realize, the more the braiding is parallel or perpendicular to the outer surface, the better will be the pushability, and the better will also be the kink resistance. So pushability gets better. Kink resistance is also there when you do a double braiding. It's like a pleating actually that you do, honestly. And they have machines that do this braiding. Okay, have you understood this? Okay, so now remember, as we come proximally, the helical braiding is shifting to a double braiding, and that too at 90 degrees to each other, so that it gives scaffolding, it allows you pushability, but the problem is it makes the catheter much more stiffer. So once it is stiff, then it will not do the third property, which is called trackability. So you understand? So the first is kink resistant, the second is pushability, the third is trackability. What is trackability? I have the wire which has gone through a very tight bend, but the micro should follow it. Now, if the micro is very stiff because of the double braiding, instead of following the wire, it will pull out the wire, because what it tries to do is straighten the path. So that is why if you see Terumo's 3 zones, we'll find that distal end is single braiding, it is more flexible. As you come an intermediate zone and a proximal zone which is actually not meant to take very complex turns. You understand? It is not meant to take very complex turns. Okay. Now, having understood this, has ProGrade got some other property that makes it the most popular microcatheter in the world even today for the peripheries? They have done a complex shift in the extrusion. And what is this complex shift? I want you to look at the cover. Now, you look at the cover, right? The distal part is 2.7 French on its outer diameter. The proximal part is 2.9 French on the outer diameter. The inner diameter along the full length does not change. It has got an ID of 0.0250 of an inch. Okay, it's 0.0250 of an inch. Now, that means the extrusion process is so different that it's able to give a thinner amount of material distally and a thicker amount of material proximally. The plastic that they use or the polymer that they use is so different. Now that is very, very complex, because you understand now you're working on a central cylinder which is going to give the lumen. Around the cylinder, you're going to push the plastic which is inside a hollow pipe. Now, thus you understand these are very different because they have to have fixed length extrusion technologies, and these make it more and more complex. On top of that, inside this extrusion, you're also doing a braiding. Have you got it? So, I hope you understand by looking at it that making microcatheters thus are very, very technically challenging. Now, the last thing is a property which is called the durameter. What is durameter? Durameter is the durability of a curve that I make on the tip of the microcatheter. Okay, if I'm making a tip on the microcatheter here and I'm going to heat it, I'm going to talk about that in a little more detail, but will it retain that shape? So I make a fantastic microcatheter, I have put braiding into it, I have done all these things. So now what happens is it is pushable, it's trackable, but it doesn't retain the tip shape. And in neuro intervention, you understand, we very often heat shape the tip. Even for the matter when we buy a product, they come sometimes pre-shaped and this shape has to maintain. So this property will depend thus on the property of the braid. Now, as you know, Terumo as a company is a company that is very, very good with nitinol. So they tend to use a lot of braiding with the nitinol. So how do you know this is a nitinol braiding? Is pretty simple. You take this material, you just wrap it around your finger. Okay, I'm just wrapping it around. And I take it out. You see the shape has not been destroyed. Have you seen that? The shape is not destroyed. Now, this is because it's nitinol. The only neurocatheter that uses nitinol for braiding is the Echelon. Okay? Or other than that, every other company uses stainless steel as the material that is used for the braiding. So why do they use stainless steel? The advantage of stainless steel is shape retention or durameter is much higher. Whereas if you're not going to use nitinol, pre-shaped catheters will do much better. That we can understand logically, isn't it? It's a thermal memory alloy, and that is why a pre-shaped catheter from Echelon will retain its shape much better. Well, let me show you some of these microcatheters to understand this property a little better. Then we will come to some other aspects of a microcatheter. Hope you understood now how they construct it, and hope you understand there are 4 properties that we look for. The shape retention is the durameter. The kink resistance is created by the braiding. The pushability is based on the fact that you use a double braiding. And then trackability is based on the fact that in the distal part, it is not double braided, but it's single braided so that it can take these loops and follow the wire. Okay. I also showed you the advantage of a braiding that is done with a nitinol braiding, that the shape will not go, it comes back to shape. And that is a very, very important property. We can actually try to cut this and see also what happens. But remember, the problem in cutting these are that these are so finely made, this might cut also. I'll just make an attempt and see what happens if we cut it. Okay, I did a bit of a cut. No, it cuts through. And that's primarily because the quality of these braidings are so good that you can, if you look very closely, you can see a braid, but honestly it's very difficult. You can see a bit of the braid sticking. Let me try see if I can pull it out. No. Okay, so you can see these are braiding and it's very, very tough. But let me show you something different now. Now I'm going to take an SL10. SL10 is a microcatheter that is used for the brain. Okay. Again, you see that property, the hub is transparent. I told you it's mandatory that the hub is transparent. Okay. So he's just written SL10. There is nothing else except the lot number. The same common construction, you will have to have this hub over here to prevent a kink. Then you have a tip that comes out here. And they again had originally just 3 zones. So you can see that this part, they gave us one more longer sleeve here to ensure that this segment also doesn't kink. Can you see that? Okay, now everybody will give this. It is nothing new. But their catheter is a catheter that basically takes a 0.17 coil, 0.017 actually, it's coil. So though they say SL10, the term 10 was just used to tell that it's compatible with a 10 coil. But in reality, this also will take an 18 coil because the 18 coils are never 18 and the 10 catheters are bigger than 10. So if we have a cover of a SL10, I'll show you what's written to make you understand a little better. So here is an SL10. So what are the things written? SL10, 2-tip catheter, because every single micro catheter will be 2-tip. They will tell you what is the gap between the 2 tips over here. And this will be 3 centimeters. I don't know, it's 6 actually between the markers. It's not normally 3 centimeters because that is, this is a 6 centimeter segment that allows you to know where the zone for detachment comes. And have a look at it. It's 150 centimeters compared to the 130 that we had with the Pro Grade. It is 1 point. It will also make you understand the inner diameter. See, what is the inner diameter? It is 0.165. So technically, though we say 10, it is actually 0.165. Much more than what we require for a coil which is 10. You understand? It's important to understand this. That's why we can push 18 coils through this, because 18 coils are 1.16. So don't be carried away just by the number. It was just for us to remember. Now this is 2.4 French distally, but here you see it is 1.7 French. See, this is what gives you the pushability. The pushability that the proximal end is actually much more thicker than the distal end, because the polymer they use is much more out here. Have you got it? So remember, when you look at the micros, you can look at each one of these parameters and look at it and decide what is what and how they are made. Now, the difference in the SL10 is technically this, that SL10 does not use nitinol but use steel braiding. Now, having said that, how can I make the profile of the microcatheter very small? So how do I make it profile very small? When I put braiding, technically what's going to happen is, it is going to make the profile thicker. So on one end, I want to reduce the profile. On the other end, I want the property of pushability, trackability, and the absence of kinkability. Okay, right? So these are the 2 markers. Honestly, they are 3 centimeters. I don't know what is that measurement. 1, 2, and 3. This is a standard 2-tip marker design. So they realized, instead of using a wire, if you use a ribbon, the profile comes down. Easy to understand, right? A ribbon is flat. So most of the winding today, in the distal end at least, is always done with a ribbon. So it's a ribbon that takes it, goes round and round. Now, unlike Yashilon SL10 will be using steel or stainless steel as the braiding material. Now the advantage of stainless steel is what? I can give a very, very good shape to it, and the shape retention is much higher. So I will just show you how to make the shapes also today. But before that, I want you to understand this property that shape retention is much better with a steel microcatheter or a steel braided microcatheter. But the problem of this is when it stays in the body for some time, the pushability capability start changing because the temperature of the body will start giving a shape to the microcatheter. For example, we have got it in multiple bends. Suppose I give these multiple loops here. And as we rotate them and keep them, and we keep it like this for some time, and I just warm it up, what's going to happen is when I take it out, you will find that this is what happens to it. Can you see that? Can you see the shape, how it's changing? I hope you get this hang. Now this, I will show with Yashilon, will not happen. So everything is a trade-off. I like this because it gives me a better shape. Steel is also good, it gives me better pushability. But when this catheter is inside the body for half an hour, it will take the shape of, so I'm going from the internal carotid, I go all the way to the A1, then I take a bend on the A1, then I've gone suppose to the A2 at distal, and you know, after some time everything is bent like this. Now when I take out this microcatheter, I cannot push it up and down, I cannot reuse it, I cannot change shapes. So those are issues. So steel continues to be one of the finest materials for braiding, but has got, see the way the shape can be changed. I can destroy this micro completely by twisting and turning it around, which will not happen. Not very difficult to get this shape. Can you get it? I hope you figure out this. So this is a property of steel. Yet every vendor in the world continues to use steel because the properties of steel is, it doesn't kink when you braid it. It is flexible when you keep it as a helical ribbon. It can be shaped extremely well with heat. But this can also have a negative that when it stays in the body, it will also fall into that. So having said that, remember, every company other than Yashilon use steel braiding. And like I said, most of the companies will use a helical braiding or just a helical ribbon distally. And as they come proximally, they will make it into a double braiding to support. And as we come more proximally, the French size will change. It will increase so that it gives us more support. Now the zones is also typical. So we will say there is a catheter with 3 zones, 4 zones, 5 zones. So remember, more the zones, better the property. So when we come to products like the XT platform, they increase the zones much more, you know. And actually when we come to the DAC-like catheters like the CAT 5, CAT 6, CAT 7, these have got 5 zones. And that is why the cost is enormous. And always the companies will let us know that they are actually not making much profit because making this is very, very difficult, right? Okay, so we are talking still on the braiding. I'll come to another property very soon. Let me just quickly show you the Yashilon. Now this is the Yashilon. Okay, Yashilon was initially made by a company. No, this is the XT. Where's the Yashilon? I will just show you an Yashilon.
Yes, it will.
So I just want to show you a micro called Yashilon. And but before, as I do this, maybe I can just show you the XT platform and they're getting it ready. So XT platform is even better because again they got a progressive extrusion, but they got the braiding quality far superior. So you look at that, this is an XT, but remember XT still works on a steel platform. So you can, if you can actually zoom onto it, you can actually see the helical strands here. These are helical, but you see the number of zones have increased. The distal helical is different, the proximal is different, and as they come down, they are changing the caliber. So as the number of zones increase, the property changes and it increases a lot more, okay? But the same problem with XT also will be, it's steel, so it is going to kink, we can be sure about this. See that? So this is the shape it's going to take because it is a steel-based system. So steel will have this problem. I kink it tight, it's destroyed forever. Okay, but yeah, ST is one of the most trackable microcatheters in the world today. It's extremely good. Even a company like Terumo that makes headway uses steel because they have realized that steel has got properties that are good for a microcatheter. So I'll just show you the Yashilon. By the way, if you see XT, this is written as XT27 150. So remember this, it basically means it's got an inner diameter which is 27. So if you have the cover of the XT, you will see the same thing written out there. I'll just show that. See that here? So you will find whatever we write over there, it's all going to be there. So XT, if you see, is a 27 catheter. It's a single tip marker. The 6 centimeter that he means over here is actually the coils or braiding that is given. It's not the 2-tip marker. 2 tips are always 3 centimeters apart. This is 1 centimeter. And here you see the inner diameter is 0.027 of an inch, right? So this is basically made for the delivery of stent retrievers and flow diverters because they require it, and that's why it's got only a single tip marker. So remember, this is very important that you understand this. Now look at the outer French size. Here it comes to 2.9 French, and here it's 2.7 French, and this is the kind of progressive tapering that will take place. And this has got nothing to do with the lumen. It is only the thickness of the coating that takes place, right? Okay, let me just show you Yashilon for a minute, and then I'll talk about another extremely important property in the construction of catheters. So this is Yashilon, right? See, this is an old catheter, still got pretty decent shape. And this decent shape comes because Yashilon is the only microcatheter that has basically got nitinol as the braiding material. The shape will retain forever purely because nitinol has got a memory. But when you try to create a shape outside the body, it will never be good. But you see, when I'm just doing the same winding, and you take it out, you find the shape retention, the bending is much less. It is more or less as good as new. See that, no? So you are not able to destroy the catheter that fast by just doing this, and you bring it out, and here it's back to new. So you understand that. So this is an advantage in a sense. Then I keep it inside the body. The shape doesn't go, so its capability of pushability continues to be retained for a longer time. But at the same time, tip shape retention is difficult. So if you want to use a Yashilon, it's far better to use the factory determined shapes because nitinol is better pre-shaped at the factory than with heat outside the body. Okay, having said that, is that the end of the microcatheter technology? What makes it much easier today to push a microcatheter? How do we reduce the friction between the wire and the microcatheter? So the simplest thing you may think is, I've got a hydrophilic microcatheter and it should go. It never happens. As we go through blends, the friction will increase more and more unless we create something that can make this resistance really drop. So inside every microcatheter, they have a sleeve. The sleeve is made of PTFE. So it's a PTFE sleeve. Now, what kind of material is PTFE? Is it hydrophilic or is it hydrophobic? Unlike the wire, which has a hydrophilic material on it, like the slippery material that we have on any wire, the sleeve is hydrophobic. In other words, it's a water repellent material. Now imagine what happens when the guide wire goes inside. A guide wire now is completely coated with water because it's hydrophilic, it's very slippery. And when the inner layer is trying to repel the water out, it is like something is pushing your wire forward. You got this point? So that is why every microcatheter today comes with an inner liner. So can you understand how complex it is? So today if you have to make a catheter, first you have to extrude and make the liners. The liner diameter will be the diameter which will determine the wire that you take. If the inner lumen is going to be 0.016 of an inch. That means the lumen of the liner is 0.016. We got it? Very complicated if you look at it that way. After the liner, they do the braiding. Then after they do the braiding, they will put the second extrusion on top of that. And the second extrusion is going to have different properties again. The distal extrusion is going to be semi-transparent with a good durameter property of allowing you to retain the shape. And as you come proximally, they will change the material completely, make it little more thicker to allow you to get better pushability, right? So if you have to summarize the way a microcatheter is made, microcatheters are extruded plastics, but not simple extrusion because they are tapered. They have got braiding. The braiding can be either steel or it can be nitinol. The distal end of the braiding is usually a spiral, most often a ribbon to bring down the profile. Proximally, it is like an X, where the X is nearly perpendicular to the sides of the microcatheter to give us stability, to give us pushability, to ensure it doesn't kink. All companies other than Yessilon, which is today a Medtronic product, it was initially made by EV3, is made of nitinol. All the others use steel, and we talked about the advantage of steel. If they are for coil delivery, you'll have two markers placed at 3 centimeters apart. Otherwise, they will have a single tip marker. Having said that, if somebody says which is the best microcatheter, most of the microcatheters available today are good. For example, EV3 did not have a good 2.7 catheter. They had Yessilon, which was not good for delivery, and today they came with a Phenom. Now, Phenom is again an extremely good microcatheter. The XT platforms are extremely good. The headways are extremely good. All of them are very good platforms. And they all work almost in the same system of multiple zones. So more the zones, better the microcatheter, because each zone has got a unique property that is for that segment of the vessel. And like I said, and as you use it and you feel it, you will come to know more and more. But among all the microcatheters made, probably Duos is the most advanced. Now, why is Duos the most advanced? If you look at Duos, you will see now this is a catheter made for coil delivery. And even when you keep it by the side of another catheter for coil delivery, you can see they managed to bring down the profile even more. You can see it even when you look in a naked eye. So they got all these properties: the braiding technology, the liner technology, the outer technology, and yet they kept the profile much lower. So if you take a Duos, if I take a Duos 2-tip marker catheter, have a look at this. We are looking at outer diameters. Now you see in all the others, the outer diameter was more than this. Have a look at it. Along with that, if you're placed by the side, maybe an SL10, have a look at this. Now this is where you can make all the difference. This is a 2.1 proximal, whereas here the proximal is 2.4. And you may say, is it very important? In terms of trackability and flexibility, it becomes very important. And the distal is 1.7 and here it is 1.6. So technically you understand what's happening is we are actually able to truly able to understand that why this is amazing technology, because he's able to bring all these components inside a microcatheter whose distal tip is 1.6 and the lumen through and through is again 0.165. Can you understand? Even the SL10 is 0.165, and that is the reason you can put even a 1/8 coil through a Duos 2-tip marker. So understand, it's an interesting property. But remember, whenever you make a catheter more and more slender, the stability of the micro is also going to be less. So it will paint inside an aneurysm very well. So when you're using soft and ultra soft coil, it's fine, but the kickback also will be more. So if you're going to use a large aneurysm, you're going to use a 2-tip marker Duos, it doesn't make sense. Because if you want to use a microcatheter as soft as this, you should be thinking of aneurysm which are 2 mm, 3 mm, where you're using ultrasoft coils or coils of that kind of rigidity so that they don't kick out, right? You get this point? So trackability is obviously going to be extremely good because it is made soft. It's got a steel braiding, so it doesn't kink, and pushability is good. Also, these are the only people thus who could also make a microcatheter which has got a single tip marker with greater length. So this is Duos, and this has got a single tip marker. Can you see they show just a single tip out here, and this has got a length which is even more, right? So this is 167 centimeters long, 2.5 French over here, comes to 1.3 French distally, but this one's ID is even smaller. It is 013. Remember, this is not a device for putting 18 coils. Even if you want to push coils through a one-tip marker, for example, if you're doing a procedure like a pressure cooker technique, you can put 10 coils through it, right? It is braided, so it has got an advantage. In other words, it won't stretch. It won't stretch like the Magic. It won't stretch like the Marathon. But yet it has got properties which are very, very similar because that Terumo or Microvention has learned to bring the profile down even more to give you a full end-to-end braided catheter that also can work like a catheter for liquid embolic agents, right? I hope you're getting the hang of this material, how we make them, understanding that all of them have a liner, an outer coating and braiding inside. And the advantage of injecting liquid through a braided catheter is that they don't rupture. And you know, if you use a catheter without braiding and you're putting pressure, there's a chance of the catheter rupturing. And if the catheter ruptures, we'll always have a problem. And that problem is you can have a devastating accident where vessels which are not intended to be blocked will block. Okay. So I hope you have got some idea about the main microcatheters that we use for stent delivery, for FT delivery, for injection of even embolic agents through the Duos, and also you understood the micros that we use for coils. So if you have a very, very tortuous anatomy, remember, Duos will go through all of them. But the problem is that it will tend to kick out also. So if you're going to use a balloon-assisted coiling out there, the Duos will work fine. But if your anatomy is not extremely tortuous, a catheter like either Headway or Echelon or SL platform, all of them will work. You know, ST platforms will all work because they give you support, they give you trackability, and they will go through. Remember, when you're looking for making your own shapes, in that case, try not to use Echelon because Echelon is nitinol based and the shape retention may not be good. So before I go into catheters that are used for liquid embolics, I will tell you also how to make shapes and what are the shapes that we commonly make for different levels, okay? So remember, every microcatheter that you have will also come with a mandrel, okay? So it will also come with a mandrel inside. These mandrels are made to ensure that you can make a shape of your choice. So try to take a straight microcatheter. It's the best. Okay, so this is the mandrel. I hope you can see it. We push it inside this and you take it down, leave it up a little, and you can decide a shape. Now you'll see, how do I shape, or what shape do I put? Most of the times a 90-degree catheter or a straight catheter will do. Rarely you may even use a 45 degrees catheter. But there are places in which this will not work. For example, suppose you're working with an ACOM aneurysm and the aneurysm is directed vertically upward and you find it difficult to get a stable position on that, or it is actually directed, say, posterior and upwards. So you may have to take a shape which is absolutely measured. That means You take the length of the A1 segment, and suppose the A1 segment is 2 centimeters, you measure it by the scale. Here's the scale. Here's the 2 centimeter. So decide to take about 4 millimeters or 2 or 3 millimeters distal to that. And now this is it. Now give the shape for the junction. So now I have created the shape. I think, sorry, it just moved back here. So here it is 2 centimeters and can be readjusted also later. Here it is 2. So you have got this 2 centimeters. So this 2 centimeters is going to tell you now that this is the A1, the ICA, this is the A1, and if I take it, give a little more length, I can now give the upward shape. Okay. Now this is the shape I want. It's exactly on the 3D. I have looked at the anatomy. After seeing the anatomy, I'm going to make a shape that will be perfectly customized and it will fit. Now the problem is, if I want to give a 90-degree shape, I will have to bend it much more. So remember this, it doesn't work like this. So I bend it here all the way up. Here I'll give a little shape here. And now I'm going to make this shape exactly customized to the shape. Now wet the micro, use either steam or a blower. We use a blower here, which we can set the temperature to 100. You do 10 seconds at a time. 10 seconds, you can wait again 10 seconds, 10 seconds, 10 seconds. 3 or 4 times you do, dip it in water, take it out, and you'll get a shape, right? Now, this is how you'll shape for an aneurysm which is coming from the ICA. Now, for example, if you've got an ICA top aneurysm, say 4 millimeters from the origin. Now in this, just change the shape. Can you understand? It's very difficult otherwise to enter. You make it this way. Have you got it? So now this length changes. So I give that length from the ICA where I want. I take the micro distally. As I pull it back slowly, it will fall into the aneurysm. Have you got this hang of it? This can get a lot more complex when I'm working on a paraclinoid location. Suppose I got an aneurysm in a point which is directed laterally, not anterior or posteriorly, and it's like the Meckel's cave, and then now I have to position it there, which I call the paraclinoid. So for that, what we often do, if the regular 90-degree doesn't work, you make the shape of the siphon. So here it is. Let's make it straight again. Imagine it's straight. Now I give a bend on the siphon. So it looks like the siphon. Then I give a right angle turn here. Okay, are you getting? I'm going to give it as a 3D shape. So here it is. I'm going to make it look exactly like the siphon. Okay, and the angle of the catheter is going to be directed this way. So this is going to be the petrous segment. This is the cavernous segment. Exits of the cavernous segment. Direct the tip based on the angio. If it is right on this side, on the left on the opposite side, and then after that I make a shape. And all these segments are heated. Now when I'm going to do this complex shapes like these, remember you need a stainless steel braided microcatheter. That's what I'm trying to make you understand. You can use the XT platform, it's fine. You can use the headway, it's fine. But you're going to use the echelon, it won't be fine because the shape won't retain. You may get some shape, by the time it goes inside the body and you shape it wrong, it's going to change. Okay, I hope you got an understanding about this. The last set of microcatheters are ones that we use for liquid embolic agents. So the liquid embolic agents also, people were amazed. They actually started braiding it from tip to tip. So Marathon basically is a microcatheter that is braided from tip to tip. But when it came to Magic, they did not braid the distal tip. So this is Marathon. Have a look at it. Very similar in some ways to the way Echelon is built. Okay. So they're giving you all kind of lengths and sizes, A, B, C, D. It goes on like this, trying to tell you D is the inner lumen. And here is D, it's 013. So why am I showing a 013? It's exactly the same lumen that was given for the Duos also. So you can actually push a 10 coil through it if you just want to put one coil. And of course, you can magic will come even lesser. So you got to look at these to understand. So when you go to 0, 1, 3, your wire has to drop and you should not cross the wire to more than 0, 1, 8, 0, 9. But having said that, because it's 1, 3, you can even use a Traxxas wire where the distal end is 0, 1, 2. So you can manipulate your wires based on this, but remember it should never go larger than this wire. And always remember, if at all you use wires inside microcatheters, especially these ones, they have to be hydrophilic or they will stretch the microcatheter and destroy it. But this itself was not good enough. This is braided, it's good. You're getting good pushability, you're getting good trackability. They brought down the distal end profile. But once it got stuck inside glue or onyx, when you pulled it out, we had a disaster. So two companies came with a detachable tip catheters. One is called a Sonic from Balt, and the second one is called the Apollo from Microvention. So this is Sonic. But here you can see they give you one distal marker and two other markers. Now what are the two other markers for? Just to tell you that do not cross proximal to the proximal most marker. So it gives you an idea. You touch the middle marker, do not come proximal. This is called fused cat because what they have done is distal to it, there is no braiding. At this junction is a weak spot. So if you pull it even mechanically, it will break. The only difference between Apollo and Sonic is that Sonic will mechanically break easily, whereas in Apollo, it's when DMSO comes in contact with the zone that the zone will dissolve, making it very, very easy to break. Apollo also has got braiding distally also, whereas Balt doesn't have a distal braiding. And so this is Apollo. Otherwise, very, very similar. Both of them look really similar. Both of them are detachable micros. Both of them have the same ID. And both of them actually does the same job. But remember, ideally in a detachable catheter, your wire should not cross 0.7 or 0.8. So the advantage of Balt is they give the hybrid wire inside it. You don't even have to think. But when you're using Apollo, you have to put a hybrid wire of 0.7, or you may actually take a Chikai's wire, whatever wire of your choice. But personally speaking, we prefer to use a hybrid. We find it an excellent wire. And I told you also what exactly is hybrid. It's a nitinol wire fused onto a stainless steel wire, and the combination is what makes it different, right? And you know, we talked in detail about it, how the distal coils are made of platinum to give us radio opacity, and we won't be going through that again. So if you're going really distal, remember, and you want a detachable tip, it's usually Sonic or it is Apollo. And today, whenever you use a liquid embolic agent, especially when you're using onyx, squid or minox, you'd use one of these. However, having said that, in our center, whenever we work with dural AVFs, where we do long injections, we tend to use duos. We find it very good. The braiding is excellent and we never have any problem pulling it out. And this segment is not a dangerous area to pull it out. But also remember one more time, there is a slight difference in the junction. Like I said, Apollo preferably would require the material to reflex back. So it's mechanical come chemical. Balt, on the other hand, is predominantly mechanical. So you should not come more proximal to the proximal most marker. Also, having said that, remember, if you're working with AVMs, by some chance, if you have come more proximal, don't panic. You can cut the catheter at the groin and nothing will happen. So this is a kind of an overview on microcatheters. I hope you understood the difficulty in making a microcatheter. The basic fundamental, they all have to have a radiolucent hub. The second thing I said, they all have a sleeve which is made of PTFE. Today they all have braiding. Yeshiron uses nitinol, all the others use stainless steel. The tip in most of the companies will be a helical braiding. The proximal zones and the mid zones will be a double braiding. And it's the combination of that that gives you kink resistance, pushability and trackability. The outer sleeve is made of another polymer. And the tip of it should also have the property of, which is called the durometer property, which allows you to for shape retention. And the combination of all these work. Whenever you take a microcatheter, remember there are multiple points where catheters have been fused together for different properties, and many of these may not be compatible with DMSO, which is the solvent that is used in the liquid embolics like Minox or like Onyx or Squid. So you have to check whether the microcatheter is compatible, the headway is compatible, the echelon is compatible, and remember that Duos is compatible. Same way, obviously, Marathon and Sonic and Apollo is compatible, but none of the Magic catheters are compatible. So make sure that you check, or for the matter, even in the periphery, if you want to use a Pro grade, it's not compatible. So that's another last thing you have to check. What is compatible with what? And if you're injecting particles, remember in a 2.7 microcatheter, you can easily inject 800 micron particles. In a 2.1, you can inject 500. And to 17, you can only inject particles that are like 100 and 200. So remember this also as you inject, because it's based on the size. So hope you got some idea about microcatheter technology. Next time you take a microcatheter, read the cover properly. When you open it, you can see the braiding that you can understand better, and you decide the segment you're going. You can appropriately choose your microcatheter depending what is your most important factor. Is it stability? Is it trackability? Or is it the flexibility of the catheter? And like I said, Duos is the most trackable, most flexible, but remember also it's got the least support. So thank you so much. I hope it has clarified some of your doubts at least.